Today we are going to learn about mastering gradient descent in backpropagation. We will explore the fundamental aspects of gradient descent, its role in backpropagation, and how to effectively implement and tune it. By the end of this video, you'll have the skills to optimize neural network performance seamlessly. Welcome to our video on mastering gradient descent in backpropagation. Today, we will delve into the intricacies of gradient descent, a cornerstone in optimizing neural network performance. You'll learn about its pivotal role in backpropagation, explore different types of gradient descent, and understand how to tune learning rates effectively. By the end of this tutorial, you'll be equipped to implement gradient descent in your own projects, ensuring efficient learning and improved convergence. Gradient descent is an iterative optimization algorithm used to minimize a function by progressively moving towards the steepest descent, determined by the negative of the gradient. Originally introduced in the field of calculus, it has become a fundamental component in machine learning, particularly in optimizing neural networks. The algorithm starts with an initial set of parameters and iteratively adjusts them to reduce the error or cost function. By calculating the gradient of this function, gradient descent determines in which direction to adjust parameters to achieve a lower error rate. The process continues until the algorithm converges at a local minimum or until it meets a predefined number of iterations. Understanding the mathematical foundation of gradient descent is crucial for implementing it effectively in neural networks, as it deeply influences the learning process and the eventual performance of the model. In the context of neural networks, backpropagation is the process used to calculate the gradient of the loss function with respect to each weight by the chain rule, efficiently computing the gradient one layer at a time in a backward pass. Gradient descent plays a pivotal role in this process by using these gradients to update the network's weights, aiming to minimize the error. This optimization mechanism ensures that the neural network learns by reducing the difference between the predicted output and the actual target. The efficiency and speed of learning heavily depend on the correct implementation of gradient descent and its parameters, such as the learning rate. A well-tuned gradient descent algorithm helps achieve faster convergence and better model accuracy, making it an indispensable tool in the training phase of neural networks. There are three primary types of gradient descent: batch, stochastic, and mini-batch, each with its unique characteristics and applications. Batch gradient descent computes the gradient of the cost function with respect to the parameters for the entire training dataset, leading to stable convergence but potentially slow updates. In contrast, stochastic gradient descent, SGD, updates parameters for each training example, resulting in faster updates but potentially less stable convergence, leading to more oscillations in the optimization process. Mini-batch gradient descent strikes a balance between the two by updating parameters using a small batch of examples, offering a compromise between the computational efficiency of batch gradient descent and the faster updates of SGD. Each type has its trade-offs, and the choice often depends on the size of the dataset and the specific requirements of the task at hand. Understanding these differences helps in selecting the appropriate gradient descent variant to optimize performance. The learning rate is a crucial hyperparameter in gradient descent, determining the size of the steps taken towards the minimum of the cost function. A learning rate that is too large may cause the algorithm to overshoot the minimum, leading to divergence, while a learning rate that is too small may result in a long convergence time. Tuning the learning rate is essential for optimizing the training speed and ensuring model convergence. Various techniques, such as learning rate schedules and adaptive learning rates, like ADAM or RM-SPROP, can dynamically adjust the learning rate during training to improve convergence. These techniques allow for more flexible and efficient learning, adapting to the needs of the model as it learns. By understanding and tuning the learning rate effectively, one can significantly enhance the performance of the gradient descent algorithm, leading to better model outcomes.
Despite its widespread use and success, gradient descent is not without its challenges and potential pitfalls. One common issue is overfitting, where the model learns the training data too well, capturing noise rather than the underlying pattern. Conversely, underfitting occurs when the model is too simple to capture the data's complexity. Poorly chosen learning rates can lead to divergence, where the algorithm fails to converge to a minimum. Additionally, gradient descent may get trapped in local minima, especially in complex landscapes, preventing it from finding the global minimum. The computational cost can also be high, especially for large datasets, making it essential to balance efficiency with accuracy. Understanding these pitfalls and implementing strategies to mitigate them is crucial in ensuring the successful application of gradient descent in neural network training. Local minima are points where the function value is lower than neighboring points but not necessarily the lowest possible value overall. They can pose significant challenges in optimization, leading to suboptimal model performance. Techniques such as momentum and Nesterov accelerated gradient help by incorporating previous gradients to smooth out updates, allowing the algorithm to potentially escape shallow local minima. Adaptive learning rate methods, like ADAM and RM-SPROP, adjust the learning rate based on the historical gradient, providing a more dynamic and flexible approach to optimization. These methods enhance the ability of gradient descent to navigate complex error surfaces, improving the chances of finding a global minimum. Implementing these techniques effectively requires an understanding of their mechanics and careful tuning to match the specific problem and dataset.
The convergence of a neural network refers to the process of the model's parameters stabilizing and the loss function reaching a minimum. Gradient descent plays a pivotal role in this process, directly influencing the speed and quality of convergence. The choice of learning rate, initialization of parameters, and the specific variant of gradient descent used can all affect how quickly and accurately a model converges. Proper initialization can provide a good starting point, reducing the time taken to reach convergence. Strategies like using adaptive learning rates and implementing momentum can further enhance convergence speed and accuracy, leading to more efficient training processes. Understanding these factors and their interplay is essential for optimizing neural network training and achieving high-performance models. In this section, we will walk through a practical implementation of gradient descent using Python and TensorFlow. We will start by setting up a simple neural network and then demonstrate how to apply different types of gradient descent algorithms, including batch, stochastic, and mini-batch. We'll explore how to adjust learning rates and use adaptive methods like ADAM to optimize the model's performance. By running these examples, you'll gain hands-on experience and see how the theoretical concepts we've discussed translate into real-world applications. We'll also analyze the results to understand the impact of different gradient descent strategies on model accuracy and convergence. This practical demonstration will equip you with the skills to implement and fine-tune gradient descent in your own projects, enhancing your ability to optimize neural networks effectively.
In conclusion, mastering gradient descent is crucial for optimizing neural networks and enhancing their performance. We have explored the fundamental concepts, different types of gradient descent, and the importance of tuning the learning rate. Understanding these elements and their implementation can significantly impact the efficiency and accuracy of neural network training. As you continue your learning journey, practice these techniques in your projects to deepen your understanding and refine your skills. Remember, the key to becoming proficient in gradient descent is continuous learning and experimentation. Thank you for joining us in this educational video, and we look forward to seeing how you apply these concepts in your future endeavors.